Good day again, Evan Snyman for Umehluko, Making a Difference. Today we are looking at the 10th video in our series on calculus, and today we'll be looking at some of the applications of this idea from calculus. So what we have seen is that a calculus thing, by finding the first derivative, and making this thing equal to naught, allows us to find a stationary point. Now, that's wonderful in terms of graphing, okay? But the old terminology for this, which was to find a local maximum or a local minimum, is perhaps more useful to us in industry. So in the real world, let's say I had a Coke can, okay? Now we know from some of our grade 8 stuff that a Coke can is cut originally from a piece of metal that is flat, that there's a rectangle of metal that actually wraps around the sides, there is a circular lid, and there is a circular base. Okay? So I know that Coca-Cola nowadays, or most cool drink companies, are making their cool drinks at 330 moles. Okay? I know that 330 moles is just another name for 330 centimeters cubed. And I know that this sheet metal needs to be cut in such a way that when I fold it and join it or weld it, that it must form that shape. Okay? I know, for example, that if I knew my radius and I knew my height, that the volume of the shape would be pi r squared height. In the same way, I know that if this is a radius, that this top piece is pi r squared, that this bottom piece is pi r squared, and that this rectangle across the middle has got a length that is 2 pi r. It is the circumference of the circle, and the height of this rectangle was simply the height of the shape. And so I know that the total surface area is 2 pi r squared, the two circles joined together, plus 2 pi r times h. And what it turns out is actually, if I was in industry, I would want to use, or given that I want to make a can that holds 330 moles, I can design that can to be tall and thin, perhaps a little bit more like a Red Bull can. I can make it short and squat, maybe a little bit more like a tuna can. I can make it as what the size that we have, which we are familiar with, which is largely driven by the size of our hand. There's an element of comfort to it, okay, from a topic called ergonomics. Well, in the industry, what I really want is to save money. And so I would want that surface area to be minimized, okay? And the way I do that is I'll set up an equation for area. I'll then take the first derivative of that equation and make that equal to naught. I would perhaps get more than one value, but one of those values would be for a maximum, and one of those values would be for a minimum. And I could use my common sense to choose which is the one I want, because obviously I don't want to use lots and lots of sheet metal. I would like to use as little as possible. So the trick here is to do what we're setting up here, is to think about this problem. If they're talking about minimum area, then we want to find an equation. Step 1 is to find an equation for the area, and step 2 to take the first derivative and make that equal to naught. Okay? Now it is not always area. It can be a whole range of different things. Okay? But what I'm talking about here is how this notion of a first derivative can be used to find a local maximum or local minimum, which actually has crucial importance in a whole range of applications in the real world. Now I know that my first example here is not a real world example. It is a graph, but it is an interesting example from a graph, so I'd like to look at it quickly. Okay. The equation of this parabola is given by 27 minus x squared. We can see that it is a downward shaped parabola, what we often refer to as a sand parabola. If C is the point x and naught, expressed in terms of x, CB, okay, well, if this is the point x and naught, then this point here would be the point x. It's in the same vertical and would be 27 minus x squared, because that is our y value. So it is x and a y value. And find an equation for the area of the rectangle. So this one's been quite friendly to us, because they've actually told us in 11.2.2 to find an equation for the area of the rectangle. Okay, so we need to know that area is length times breadth. And so we would be thinking that actually from what we've just done in CB, that height there, okay, would be 27 minus x squared. And hopefully what we're realizing is that that length there from C to D will be 2x. So in this case, our area would equal 2x times 27 minus x squared, which in this case would equal 54x minus 2x cubed. And that is our answer for 11.2.2. However, we have a follow-on question that's quite important, and that is to determine the area of the largest. Now again, they have used the word largest here, but they mean maximum. Okay, so we want to have the maximum rectangle, the maximum size for this rectangle. And so what we're going to do is we're going to take the first derivative for this area, which in this case would be 54 minus 6x squared. And what we're going to do is we're going to say, lovely, this thing must equal naught. We can solve it by saying that therefore 54 equals 6x squared, 9 equals x squared, so plus or minus 3 equals x. Now, yes, because of symmetry, the minus 3 does make sense, okay? But in many ways, we would discard it and say, because we are talking about C being on the right-hand side here, therefore the x value of C is 3, and as a result, our largest area, our maximum area, will be when we have 3 going in here, which is therefore going to be 54 times 3 minus 2 times 3 cubed, which equals 172 minus 54, which hopefully is, no, I like is 162, I'll fix that now, is 108. Because we're talking here about, do they give us any units? I don't see any units in the question, so we're just going to say the area here would be units squared. I need to fix that little typo there, so that 172 should be a 162. Apologies. Okay, so here we have quite a simplistic, simple example, even though it was using graphs and this notion of the area underneath a parabola. Okay, we set up an equation for the breadth, we set up an equation for the height of this parabola. As a result, we were able to work out the area underneath the curve given by this rectangle. And as a result, we were able to take that equation for the area and take its first derivative to find the maximum area of this rectangle. Okay, let's have a look at another example. We have a water tank. Okay, they don't really make it clear, but it does. I'll suggest that this water tank is some form of cuboid, that it is rectangular in shape. Okay, so we've got some sort of shape that is our water tank. Okay, cool. It is governed by the equation that the volume equals, okay, the volume of water in this tank is given by 5 plus 10t minus t squared. So actually we're not talking about the tank itself, we're talking about the amount of water that is sitting inside this tank. How much water is inside this tank? Okay, find the rate at which the volume is increasing when t equals 2 minutes. Now, rate, okay, is always a comparison of two values. So what we're talking about here is, again, the first derivative. Okay, so rate here would be v dash. Okay, so as a result, 9.1, v dash would equal 10 minus 2t Okay, well, we want to measure it at t equals 2. So we've got 10 minus 2 times 2. Okay, so v at 2, which would therefore be 6. And again, we're talking about volume and minutes. And they haven't told us what the volume is measured in, so we have got 6. It was volume, they didn't tell us it was cubic meters or something, so it's 6. Okay, the rate at which the volume is increasing by 6. Now, what we do know is that because this value is positive, we would see this as be an increase in volume. Okay, so the volume is increasing because we have a positive change. Okay, again, hopefully that makes sense to you. Okay, at what time does the volume start decreasing? Okay, so if it's going to start decreasing, we need to look at where does v dash equal 0, because where it equals 0, we'll have a change from positive to negative. So over here, we're going to look at 9.2. Again, it's a slightly unusual example. And what we have here is that v dash equals 10 minus 2t, and it equals 0. As a result, okay, we're going to take this across, and what we have here is t equals 5. Okay, which makes sense because if it is increasing at 2 minutes, then it is increasing before 5 minutes, and so after 5 minutes it will start decreasing. Okay, and so again, that makes sense to us if we think about it, because you've seen here from our first sum that you could see here that at 2 minutes the thing was increasing by 6 units. Okay, they didn't tell us whether it was meters cubed or whatever the case is, but we do know that volume is often measured in liters or meters cubed or something along those lines. And so when we reach t equals 5, it used to be increasing, and so now it's going to start decreasing. Below t equals 5, it was increasing, and after t equals 5, it was decreasing. And again, that sort of makes sense. We've got a negative t squared. The negative t squared leads us to have something along those lines with a negative parabola, where in this case we know the turning point will be at 5. Okay. Moving on to our next example. This is a much more typical exam question. Okay, it comes from a much more recent exam paper, as you can see by the font of the text. They don't expect you to know the volume of a sphere. That's the good news. They don't expect you to know the volume of a cone. That's good news. And they do here give you the equations here in the highlighted block. Okay, calculate the volume of the sphere. Okay, we are told that the radius of the shaded circle, okay, is 8. We're told that the height of this thing is okay, cool. Find the volume of the sphere for 1 mark. So all we're going to do is we're going to plug in this value of 8, which is our radius. We're going to plug that in over here to our formula. And so we've got volume equals 4/3 pi times 8 cubed. And that gives an answer of, I don't know, 4 divided by 3 times 8 cubed times pi. I'm getting an answer of I had an answer initially of, where's my cursor gone to? And the answer initially of 2048/3 pi, written as a decimal, is approximately equal to 2144,66. Okay, show that r squared is this value here. So let's have a look at what they're talking about here. R squared equals 64 minus x squared. So again, if I was to look at this triangle in the center here, in terms of Pythagoras, okay, I would realize that 9.2, that x squared plus r squared, in this case, equals 8 squared. Please don't confuse the r of this diagram, which is the radius of the gray circle, with the r that we had just now, which was the radius of the sphere. That's partly what they're trying to do here, so trying to confuse you a little bit. Stay brave and make sure you keep track of which radius is which radius. As a result, r squared would equal 64 minus x squared, as expected. Okay, determine the ratio of the largest volume of this cone and the volume of the sphere. So we just need to be careful because this is a slightly unusual question. They're asking us to find a ratio. We'll keep track of that for the end. You're being asked to find the largest volume of this cone. So let's have a look at the volume of this cone. The volume of this cone is equal to 1/3 pi r squared times the height. In this case, we've got 1/3 pi times, well, in this case, our r squared value is 64 minus x squared, and that came from over here on the right, because we knew that r squared was 64 minus x squared. Okay, and then hopefully looking in on the diagram, you can see that the height of this cone is going to be x plus 8. And so we have a height of x plus 8. Now, what we need to do here is to multiply this out. Okay, and so what we're going to get here is 1/3 of pi times 64x minus x cubed. 64x minus x cubed plus, what's 64 times 8? 512 minus 8x squared. And so what we're getting here is a real interesting value here of 64 pi over, so let's write it in order. So let me just write this in better order. Okay, so minus 1/3 pi x cubed minus 8/3 pi x squared plus 64 over 3 pi x minus, plus 512 pi over 3. Now, we were talking about the volume of this largest cone. So what we need to do here is we need to take the first derivative to find the largest cone. Do we? Okay, so we need to find the ratio between the largest cone. So therefore we need to find the largest cone, we are looking for the first derivative. So the first derivative is going to equal 0, equals 3, this 3 comes to the front, we get minus pi x squared, this 2 comes to the front, so it's minus 16 over 3 pi x, this comes to the front and becomes plus 64 over 3 pi. Now we can divide through by the pi, so I'm going to just create some space here to keep working. As you can see, this is a 7-mark question. It's meant to be quite difficult. So I'm going to divide through by minus pi. So divide through by minus pi. Okay, so what I'm going to get here is, again, an answer of 0 equals x squared plus 16 over 3x plus 64 over 3. Again, I can choose to multiply through by 3. But what I'm going to get here then is a x value, which again, I'm not going to be able to do so easily. So let's have a look here. I'm going to times through by 3 this time, just to make my life a little bit easy to try and solve it, because what I'm hoping is that it factorizes, which at the moment it is not becoming apparent to me. So 0 equals 3x squared plus 16x plus 64. Okay, I should have done here. I've times by minus pi, so this should mean again, glad that I checked. That should mean just fix that quickly. So that should have been minus 64 over 3 and minus 64. So again, let's go back here. and it's telling me that I'm going to get an answer of x equals 8/3, or an answer of x equals -8. Now think this through. Okay, my x value can't be negative, so I can discard this value. Okay, so therefore this is our correct answer, x equals 8/3. So now we need to go back and plug that into our equation. So therefore our volume maximum would be equal to, okay, so let's go and work this thing out. 8 divided by 3, so mode 1, I'm going to store this value in my calculator, so 8 divided by 3 equals, I'm going to store it on my calculator as a value. So I've got minus pi divided by 3 times this value cubed, minus 8 divided by 3 times pi times this value squared. So now this is calculator work. Sometimes it's quite tedious, so be careful we don't make a silly mistake. Plus 64 divided by 3 times pi times this value, plus 512 divided by 3 times pi, and they give me an answer of 635.45. Now already that would have been quite a significant sum, but again, I want to encourage you to make sure we go back and read the question, and they ask us for the ratio between the largest volume and the volume of the sphere. So in this case, the answer would have been 635.45 ratio. So this is the ratio of the volume of the cone to the volume of the sphere. To 214.62144.66, and what I want to quickly just check is, no, it doesn't. So let's have a see. 2144.66 divided by 635.45 equals nothing nice. So that actually does not simplify down, which is what I was just checking. And so that actually, that weird value there, is our answer, the ratio between the largest volume of this cone and the volume of the sphere. So all we have here is our final answer. It was an unusual question. Thank you for your time. Have a great afternoon.